Hello, everyone. Today we are going to discuss representations of functions as power series. Actually, from previous section, we already know one representation. Remember, last class I was showing you the simplest power series, which was looking like x to the power of n and from 0 to infinity. And in extended way, it was looking like 1 plus x squared, like a long polynomial with all coefficients equals to 1. And using standard geometric series sum formula with the first element equals to 1 and the ratio equals to x, we were getting like 1 divided over 1 minus x. So actually, that the first function we can represent as a power series is function 1 over 1 minus x, and the power series is going to be very nice, simple power series, right? We should remember that this series is convergent only for x less than 1. And we are not going to worry about endpoints for right now. We are just going to kind of be interested in radius of convergence. Now, can we represent some other functions as power series? For example, can we represent something like this? 1 over 1 minus x squared as power series. Just imagine that instead of x here, you use x squared and plug it into your formula. So instead of x, you put x squared to the power of n and from 0 to infinity. You know that power and the power is a product, and you are going to have x to the power of 2n here. Easy, right? Something more complicated. How about this one? 3 minus x. Can we represent this one? Yes, there are two ways to represent this one. So way number one, we'll need to modify this denominator to bring it to the shape of 1 minus x. How we do this? We are going to take 1 over 3 outside of parentheses. Something like this, right? And then 1 over 3 sits by itself, and this one is going to use a new x over 3. Right now, it's over 3 here to the power of n, like we have it over here. And from 0 to infinity. And in some books, they will bring this 1 over 3 inside. And in denominator, it means that the power of 3 is not n anymore, but n plus 1. And you can have the answer looking like this, x to the power of n, 3 to the power of n plus 1, and from 0 to infinity. If you leave your answer like this, I'm going to accept it too. As I said, there are going to be two ways, right? What is going to be way number two? Way number two, guys, here is going to imagine that this is going to be series with center not at 0. For example, I represent it as 1 minus x minus 2. Can I do this? Well, if I simplify it, it's going to be 1 minus x minus 2, and this minus kind of becoming plus, and that's going to be 3. So here, instead of x, I will substitute x minus 2, and that's going to look like sigma x minus 2 to the power of n, and from 0 to infinity. Even easier, right? So what is the difference between these two series? This centered at 0. This one centered at 2, right? The center of this series is 2. Well, it's going to depend on our task or our problem we are trying to solve, and to define like what kind of series we want, centered at 0 or centered somewhere else. And you will understand it a little bit later. Okay, so what we can do to the series, actually why people like this series. There is a theorem which tells us that if you are dealing with convergent series, you can actually integrate and differentiate this convergent series. And integrals and derivatives are going to converge to a function, and it's going to always going to work on the same radius of convergence. I don't want to write down the theorem. It's kind of long. I'm just going to show you examples, okay? For you, just remember, if you have a nice convergent series, you most likely will be able to differentiate and integrate it. And the radius of convergence is going to be the same for the integral and for the derivative. I'm going to do both on this one, 1 over x. So I'm going to write down differentiate. So 1 over 1 minus x equals sigma x to the power of n, and from 0 to infinity. How will we differentiate it? Well, here, we differentiate it just using standard rules of differentiation. It's 1 minus x squared, right? Because it was minus 1, like the power, and there is minus 1 from x, it's going to be plus 1. This minus is going to cancel. How do we differentiate this? We just differentiate this term as a function, like a power function. So we're going to have sigma n x to the power of n minus 1. Remember, power function. And I'm going to change the index of my series to 1. Why? I'm going to write down this series. It's 1 plus x squared, extend it a little bit. If I differentiate it, derivative of 1 is equal to 0. And my 0 term is going to disappear. I'm going to start my terms, I think, with this one. Derivative of this is going to be 1. Okay? So, integrate. I'm going to do the same. 1 minus x equals a series. And kind of put integral on both sides. Integral here, dx, and integral here, dx. Here a little bit interference of n with integral sign. So what is going to happen over here is going to be what? Well, we know that's ln of 1 minus x. Maybe with minus, extra minus here. Because if you differentiate ln, it's going to give you like 1 over 1 minus x. But if you differentiate negative x, it's going to give you extra minus. So we'll kind of apply for it. And maybe plus a constant, right? What are we going to have on this side? Well, I'm going to integrate each term of this power function. So kind of switching integral and sigma. We can do this when everything is convergent. So we can switch integral and sigma if everything is convergent. And equals 0 to infinity. I'm going to do the integral like over here, continue. So when I integrate x to the power of n, I know that I'm going to get x to the power of n plus 1 divided over n plus 1, right? And from 0 to infinity. Here, nothing is going to disappear because when you integrate 1, it's going to give you x. Now, it is going to be the constant. We already kind of got everything. The function equals to the series constant. Constant is a question. How I'm going to figure out the constant? I'm going to plug in certain x into my expression. I'm going to plug in x equals 0 into my expression. It's supposed to be a true statement. So minus ln 1 minus 0 plus a constant equals sigma 0 to the power of n plus 1 and from 0 to infinity. Well, sum of zeros is going to give me 0. ln of 1 is equal to 0. So my constant is going to be 0 plus constant equals 0, from where constant equals to 0. So my constant is going to be equal to 0, and I got a very nice representation. Ln of 1 minus x equals sigma n equals 0 to infinity n, x n plus 1 n plus 1. Interesting story, guys. In Newton's time, when he was just developing calculus, there was no function of logarithm. So when Newton ended up with finding integral like this, he could not write down ln because ln was not kind of used at that time. But he knew that this function can be represented as a series, and he did it and integrated this series, and he got his answer as a series like this. He did not know ln yet, and ln was kind of invented a little bit later. So kind of series is like nice to integrate and differentiate. You probably guys see it like that. It's very nice to integrate and differentiate, right? As the power function, we know how to integrate and differentiate it well. Okay, now what other series we can kind of develop using this integration and differentiation technique? I'm going to do one more example just to show you some interesting relations between series and functions. You know, guys, that is going to be example. I don't know. Don't remember. I did not label them. Okay, I'm going to do example number 1 here. So, guys, we do know that integral dx 1 plus x squared is equal to what? Tangent inverse of x plus a constant, right? How do we know this? Well, that's if you differentiate tangent inverse, you get this 1 over x, 1 plus x squared, right? But you can represent this 1 over 1 plus x squared as a series, right? Just how the series is going to look. Minus x squared to the power of n from 0 to infinity. Why it's minus x squared? Because original series has 1 minus x. So instead of x, I'm going to put negative x squared here. Okay? And I'm going to simplify it. It's going to be minus 1 to the power of n, x to the power of 2n, and goes from 0 to infinity. Guys, here, I don't want to integrate this expression in general. It's going to be way too long. I want to actually write it down first in numbers and maybe then do it in general. But I don't know. Maybe I should integrate it. Let's imagine that we have integral of this and the integral of this. Well, general is not going to be that bad, right? Sigma minus 1 is not going to be integrated just because n is like index of summation, and we're going to integrate only x, right? So x has power of 2n, so we add plus 1 and 2n plus 1, and I think that's it. We integrated it. Such easy job, right? We are going to make this series representation equals to tangent inverse. It's supposed to be equal to tangent inverse of x plus a constant from over here, right? Because we kind of represented this as a series and then integrated it, and it's supposed to be equal to tangent inverse. Now you probably ask me, what is interesting here? Well, let's figure out the constant first. Again, I'm going to plug in x equals 0. Why? Because all these terms are going to become 0, 0, 0, 0. And I'm going to have tangent inverse of 0 is also 0, so the constant is equal to 0. Now I'm going to use this representation to show you interesting fact about tangent inverse. Guys, I'm going to actually write down the terms of this series. So I'm going to set up n equals 0. N equals 0, this one is going to be positive, and this one is going to be x, and this one is going to be 1. So we are going to just have x. And then when equals 1, it's going to be negative, and that's going to be x cubed, and that's going to be divided over 3. Minus x cubed over 3 plus x to the power of 5 over 5. It looks like we are going to have only odd powers because this is actually general way to write down odd number. Okay, minus x to the power of 7 over 7, and so on, right? Now, guys, we have actually one more series representation for one more function, tangent inverse. We just represented tangent inverse as a sum of series, right? What we can do with that sum of series? Let's plug in, instead of x, 1. How about set up x equals 1? Let's see how this is going to change. So what we have? Tangent inverse of 1. What is tangent inverse of 1? In general, tangent inverse, it's like angle which gives you tangent equals to 1. You probably remember that tangent of pi over 4 is equal to 1. 45 degrees, tangent equals to 1, right? Here we are going to have a sum 1 minus 1 over 3 plus 1 over 5 minus 1 over 7. And guys, what we have? It's a representation of number pi. Remember, usually we use representations of number pi from geometry. This was one of the first representations of number 5 coming from calculus, binding like or connecting geometry and calculus. You see, this representation of number pi is not the super good one because it takes long amount of like time to add up all these terms to get some kind of decent accuracy for number pi. So you'll need probably add like maybe 100 numbers here to get just like 3 digits, or after that, that's no point. But still, this is called Leibniz formula. Leibniz formula for number pi. If you multiply it by 4, you are going to get like pi represented like through the sum of series. Okay. How else people are using like series besides like, converting them like and using for integrals? I'm going to consider one more example of use of power series. Um, and of course, we are using them in many more ways, but this is just the beginning. Let's consider example number 2, and that's going to be integral of 1 over 1 plus x to the power of 5 dx. And somebody wants to find definite integral. If you recall chapter 7 where we learn integrals, these type of integrals are non-elementary function. Means that actually there is no formula answer for this integral, non-elementary function. Oh, well, if we still need to calculate it, we can do it numerically like we learned when we did approximate integration, or we can try to use a series. Let's see how the series are going to work in this case. So guys, on step number 1, I'm going to represent the function under the integral as a series. Well, you probably remember that it's supposed to be minus x. So I'm going to have minus x to the power of 5 to the power of n, and n will go from 0 to infinity. I'm going to simplify it a little bit, okay? I'm going to write down like minus 1 to the power of n as a separation, minus to the power of n, right? And then x to the power of 5n. N goes from 0 to infinity. After I did this representation, I'm going to take the integral. I'm going to integrate it. Well, you understand that we are not going to integrate minus 1 or sigma, so I'm going to keep sigma and keep minus 1. I'm going to integrate just expression under the integral, and that's going to give me what? X to the power of 5n plus 1, very easy, 5n plus 1, because it's a power function, very easy to integrate, and plus a constant, right? But because we do have a definite integral, we probably don't need a constant, we just need to do substitution. So I'm going to eliminate the constant and do our substitution 0 and 1. Why? Because the integral which we tried to calculate was a definite integral. We needed to find the area under the curve. Well, not very difficult to plug in 1 and 0. Sorry. So I'm going to keep sigma, going to keep minus 1, and I'm going to plug in 1. 1 is going to give me 1 over 5n plus 1 here. If I plug in 0, I'm going to just subtract 0 from here. And that's it. So actually, I got a very nice series, minus 1 to the power of n, divided over 5n plus 1. N goes from 0 to infinity. Well, we remember that for this series, we can use like some first terms as estimation of a sum, and that's going to give us like value sum. Maybe it would be a good idea to see like, because it's alternating series, how many terms we want to use to reach certain accuracy. I'm going to write down first few terms. N equals 0 is going to give me actually 1 over 1, right? N equals 1 is going to give me 5 plus 1, 6, and minus 1 over 6. Then plus 5 by 2, 10, 11. So 1 over 11 minus 1 over 16 plus 16 was 3, 4, it's 1 over 21. And so on. This is alternating series. Yeah, remember that remainder of alternating series is less than the first term you drop. Imagine that we want to drop this term. We want to add up 4 terms, which is not very difficult using calculator, but we want to drop term 21. So how much we drop, or what is going to be remainder? Well, for example, this term is 1 over 21 is going to be approximately equal. Let me do the division. It looks like it's going to be about 0.05. It's a little bit less actually, but you see that if I continue count only 4 terms, which is not difficult to do with a calculator, right? And it's much easier than numerical approximation, if you wish. I'm going to get very good accuracy, like at least 1 digit after decimal point. Okay. Well, we can probably calculate what it's going to be. 1 minus 1 over 6. I'll try to calculate it. Give me a second, guys. Yeah, I use the calculator and my sum of 1, 2, 3, 4 terms is going to be approximately equal 0.86. Well, maybe 6 is not a good estimation already because our error is 0.05, but I'm going to write it down. Okay. So 4 terms. If you need better, like, next term, for example, is going to be 1 over 5 here, 25, 26. Well, still not kind of good, right? If I want to get for sure this last digit, I'll need at least like 1 over here, which is supposed to be division by 100 here. And 100 is probably around like 20, so 20 terms. Well, 20 terms is not that good in comparison to numerical approximation, which probably requires same amount of terms. But it's just one of the ways to use to estimate number of like definite integrals, for example. Okay. Well, there are more ways to use power series, but we are going to learn about them next in next section when we work with Taylor series. For this section, we are done and kind of do your homework and see you in our next lecture.